So we'll start today's lecture with the absorption probabilities. And we have already gone through a bit of it, but let me quickly recall the notation. So the general setup goes like this. So we decompose the state space into its canonical decomposition, namely this T is the set of all transient states, and then C1, C2, etc. are the closed and recurrent classes. So these are recurrent classes which are closed essentially. Now we defined tau to be the exit time of T. This means this is the first time first m bigger than or equal to 0 such that xm exits T. So xm belongs to T complement. So in general, there is no guarantee that this tau would be finite with probability 1. So we make an assumption. We assume that for all state I, the under Pi, under the probability Pi, tau is finite with probability 1. It can be shown that this is the case when the state space is finite. In general, it's not obvious, but when the state space is finite, this is true. Now, for all I in T, for all transient state I and for all recurrent state K, we defined uik to be the probability of x tau to be equal to k under the probability pi. So this means the Markov chain that starts from I exits T because of hitting the state k. Okay. The chain starting from I exits T because of hitting the state k. So in other words, the chain that starts from I hits T complement first at the state k. K is in T complement. Then we partitioned the transition matrix P as this QR0 and P2. But Q is the restriction of the matrix P to the states in T. Okay? On the other hand, R is a matrix of transitions from states in T to the states in T complement. This 0 is essentially the other way around. This is transitions from recurrent states to the transient states, which obviously is 0 from once you're in a recurrent state. In 1 year, once you're in a recurrent class, you are absorbed in that class. Right? So therefore, it's because the recurrent classes are closed, and therefore the probabilities are all 0. Once you're in a recurrent state, you cannot go back to a transient state. On the other hand, P2 is a matrix that gives you the transitions between the recurrent states. And as we argued last time, these so-called absorption probabilities, these UIKs, the computation of those will not involve P2 at all, because this is about reaching the first recurrent state only through transient states. So Q and R will completely determine these probabilities. So define U, the U is a matrix of UIKs, where I runs over transient states and K runs over the recurrent states. This is the matrix of absorption probabilities. Okay. The UIK is this probability here for this chain. Now, we are using the phrase absorption probabilities in a generic sense because it's not necessary that the chain will get absorbed at the state K, but the chain will definitely get absorbed in the recurrent class containing K. And therefore, these absorption probabilities are going to be obtained from these UIK. So that's why these are, we'll abuse our terminology and call these absorption probabilities. Now, the theorem that we stated last time was that under the notations and assumptions as above, so essentially it means that mainly this assumption holds. Without this assumption, the UIK is not even well defined. So therefore, we'll assume that this holds. So U is given by QU plus R. And you can note that this matrix multiplication, all the orders will match and so on. There is no problem. So when the matrix I minus Q has an inverse, then U equals I minus Q inverse times R. By the way, I minus Q inverse, as we discussed last time, is called the fundamental matrix. And this fundamental matrix plays a very important role in, the theory of Markov chain, and in particular in the computation of absorption probabilities. And one example where this fundamental matrix exists, in other words, where I minus Q has an inverse, would be when the number of transient states is finite. I gave it as an exercise last time. If T is finite, then Q is actually a finite dimensional matrix. And then since Q power n would be summable entry wise, I minus Q will indeed have an inverse. Okay. So I asked you to check all these things. So therefore, in particular, when you have a Markov chain with a finite state space, then obviously T is finite also. In that special case, you can use this formula. U is I minus Q inverse times R.